Swayam Prabha. Digital India. Educated India.
Okay, so we'll continue with the discussion last class that we talked about definition of a random variable and how do we define a random variable with its set of values and probability distribution function, and some examples also. Okay, we'll continue from there. So here I am introducing a bivariate distribution. Okay, so we also said that a random number can be a vector, it can have multiple components, then the associated distribution will be multivariate. But here I am talking about bivariate, meaning there is going to be two variables, two random variables, and we are looking at distribution of that. So we say this x is a vector and it's a random variable which has two components, x1 and x2. Random variables are always expressed in terms of capital X letters. Okay. Then we say that the probability distribution P2 x1 x2. So this 2 means there are two variables inside. Okay, this suffix will always mean that how many number of arguments are here. Okay, there are two variables. This small x1, small x2 are the realization of the random variable. This x1 can take small x1 value, it's a numerical value, and this x2 variable can take the small x2 value. So we use small letters to denote the numerical value the random variable can take. And this distribution we call it as a joint probability distribution function of x1 and x2. Okay, so this word joint is important because it gives a combined distribution of how you simultaneously can realize both x1 x2 of a given value. Okay, that's why it's called joint distribution function. And the physical meaning of the joint distribution function is that the probability that x1 will have a value between small x1 and small x1 plus dx1, at the same time the second variable x2 will have a value between x2 and x2 plus dx2, that is given by the joint probability distribution function times dx1 and dx2. We had a similar description for a single variate distribution function also, okay, in the same way. And from bivariate, if you want to extend to multivariate, you will do the same thing. Now, once we have defined the joint distribution function, we can also define some other subsets. Okay, for example, you are interested in what is the probability that x1 will take a value of small x1 regardless of the values of x2. x2 can take any value. Okay, you are not worried about the distribution of x2, you are only looking at what is the probability that this random variable will take a value of x1, and that is defined or obtained by integrating the joint distribution function over all possible x2. Okay, so here I am interested in only finding the probability of finding x1 regardless of the values of x2, so that you obtain by integrating out all possible x2 values. So this integration is over all possible value of x2 for a given x1, and this is called the marginal distribution of x1. Okay, it's a kind of a subset, and the notation for marginal distribution is this p1 of x1. This one means there is only one argument, and we put x1 here because that is our interest. You can also similarly write a marginal distribution of x2, that would be p1 x2. In this case, you will be integrating out all the x1 values. Okay, so you are interested in only the marginal distribution of x2 regardless of the values of x1, then you are going to get by integrating of the joint distribution function over all possible values of x1. So we call this as marginal distribution of random variable x2. Then there are other scenarios where sometimes we specify the value of one variable and what's the probability of finding the other variable. Okay, so we are going to condition the statement. Okay, so we can ask something like this. Let's say I am specifying the value of x2. Okay, the random variable x2 is taking a particular numerical value, it is given, it is prescribed. Given that, you ask what is the probability that x1 will take a particular value small x1. Okay, so then we are making conditional statement. Okay, and this leads to the definition of conditional probability, and we denote it with this notation. Okay, this 1 over 1 basically means I am conditioning one variable and I am asking the distribution of other variable. Okay. Since it is a bivariate, I can only specify one and I can have a free variable other one. If I have a n number of them, I have a lot of possibilities of how many I can fix and how many I can find out. Okay. But in this case, 1 bar 1 basically means I am specifying one variable and I am asking the distribution of the other. Okay. And the notation goes something like this. Whatever we are prescribing, we put that, okay, we condition this with this bar and then we ask what is the distribution of x1. Okay. So, you should get used to writing probability distribution function like this. Okay. Joint distribution, marginal distribution, and here we are talking about conditional distribution. Okay. And those important terms I have highlighted and underlined. So, this basically gives you the, it basically describes, it is basically a probability distribution function for finding x1 with a condition that x2 has been prescribed to a value. So, now once you have this conditional probability and the marginal probability, marginal distribution, you can also construct your joint distribution function. How? If you look this, so this is the marginal distribution of x2. It gives me, regardless of the value of x1, what is the distribution of x2. It specifies the condition. Once I take this x2 and I condition it and I find what is the probability of x1, the product of these two is nothing but our joint distribution function. Okay. Sometimes we know these two and we want to find this, or sometimes we know this and we know the this conditional probability and we want to find the. So, you can see the relationship between these three distributions: joint, conditional, marginal. Okay. Now, we can also make some more statements about the these three functions depending upon whether these random variables are statistically correlated or statistically dependent or not. Okay. For example, there are some instances where the two variables can be statistically independent. So, when I say statistically independent, what it means is the occurrence of one variable is not controlled by the other and vice versa. Okay. These are two independent variables. Then the joint distribution is nothing but a product of the individual distributions. Okay. So, you can see that this P1 means I am talking about only the distribution of one variable. This will be a different function and this can be another function. The product of these two will give me the joint distribution function only when x1 and x2 are statistically independent. And if you compare this expression with this general expression, you will see that the conditional probability is nothing but the marginal distribution itself. Okay. Now, here is an example. If you think about a Brownian particle in 1 dimensions, you can specify this particle with its position, current position and its velocity. Okay. And you can ask what is the joint distribution, and there are theories to derive this. The joint distribution function of x and v, position and velocity in 1 dimension, happens to be a product of two Gaussian. Okay. So, the x variable, the position is Gaussian distributed and so is the velocity also. Okay. So, here is an example of the independence, the statistical independence I was talking about. The position of the Brownian particle is independent of its current velocity, and similarly the velocity is independent of where the position is. Whether the particle is here or there, the velocity distribution is independent. Similarly, whether the particle is moving faster or slower, it does not depend, doesn't affect its current position. Okay. So, again there are some cases where they may be dependent, okay, but we are talking about one specific time scale where one can derive this equation. Then we basically have this example that I can write the joint distribution function as a product of the position and the product of the probability of the velocities. And so, here you will see that there is this variance. So, the mean position x is 0, mean velocity is also 0, but the variance of position and velocity, they are related to the diffusivity and the temperature and so on. Okay. So, these things we will see later on. So, next what I am going to do is, having introduced the bivariate, now I will extend this to multivariate with more number of variables and define the same set of functions: joint, marginal and conditional. Only difference you will see is this index I am going to change, okay, because I am going from 2 to some n number of variables, and that is the only difference. And in this course, this joint distribution, marginal and the conditional probability, these are all very important elements for our understanding. So, it is very important that we understand the meanings and the relationship between these distribution functions. Okay, so Okay, so here what we are saying is the multivariate distribution over r number of variables. So here I have a random variable x with the components x1, x2, x3 all the way up to xr. Okay, so and then we can call the probability distribution P of r. Okay, r here because there are r components here. Okay, this is called the joint distribution of all the random variables x1 to xr. So we are just extending the definition of bivariate to a r variate problem. And this function PR x1, x2 all the way to xr and then dx1, dx2 all the way up to dxr, this basically gives me the probability that the first variable will be found between x1 and x1 plus dx1 and x2 at x2 to x2 plus dx2 and so on so. Okay. And then we can also define what is called this marginal distribution. Let us say there is a sum set S less than R. R is the total number of components, and you can take a value S which is less than R, and we can say what is the probability distribution of finding the first S variables values, okay, and that you obtain by integrating the total distribution function over the remaining degrees of freedom. Okay. So up to S you want to get the probability, from S plus 1 to XR you are basically integrating over. Okay. So last time we had only 2, we specified one and we asked the distribution of the other, but here we have R number of variables. Of this R variables, I am only interested in the first S variables. The remaining S plus 1 to XR R variables I am integrating it out. Okay. Here I show only one integral symbol, but actually you will have R minus S number of dimensionality. Okay. So having defined the marginal distribution, we can also ask about the conditional probability, that you can probably specify xs plus 1, xs plus 2 all the way up to xr. Okay. So you are only interested in finding what is the probability of finding x1 to xs, having specified the remaining ones. Okay. So the remaining ones are s plus 1, s plus 2 and all the way up to xr. Okay. So this basically brings us to the definition of conditional probability for a multivariate distribution. So here you can see that I am interested in the distribution of S number of variables, having defined R minus S, having prescribed R minus S. Okay. So that is a notation. How many you fix should be in here, and the number of free variables should be here, separated by this vertical line. That is the notation. And you can see that here I am listing all the S variable here and the remaining R minus S variables here. Okay. This is the conditional probability, and we can also combine the marginal distribution and the conditional distribution to construct the total distribution function. Okay. So you say what is the marginal distribution of R minus S variable, that is this. How do you get this one? You will get this one by integrating out the joint distribution function from x1 to xs. Okay, this opposite of what we did here. So you will get a marginal distribution of all the remaining S minus R variables. Condition to this prescribed variables, you have this conditional variable. When you take a product of that, you get a total distribution function. We can also define the moments of multivariate distribution. So here since I have R number of random variable, and I may write a moment function, and here each variable has its own moments. Okay. So x1 has m1 moments, x2 has m2 moments, so on so. Okay. They need not be the same. you can choose 0 here, 1 here, 2 here and so on, so okay, depending upon what you want to obtain. In the case of, let's say, the Brownian particle, you may wanted to know what is the first moment of position and the first moment of velocity, or you may want to find the 0th moment of position and the second moment of velocity, so on, so okay, different combination is possible. So the way you obtain that is you need to integrate the joint distribution function weighted by the moments raised to the power of each of these variables, okay, and then it's integrated out. So here are some useful relationships that we may be interested in. So when we look at multivariate problems, multivariate distribution functions, if you have sometimes we try to we write functions of random variables. Okay, for example, x1, x2 are two different random variables, and with its own distribution function. We may be interested in another random variable written as a sum of these two. Okay, so then you can say what is the statistical properties of y. Now, since in this case y is a sum of two random variables, we can say that the average of sum is the sum of the averages. So you can get an individual average of x1 and x2, and if you add it up, that is nothing but the average of the average of the sum itself. Okay, this is regardless of whether x1 and x2 are statistically independent or not. Okay, as far as the mean is concerned. Whereas if it is when we look at the variance, only if x1 and x2 are independent and uncorrelated, then you can add up the individual variances for the sum. Okay, this is always true. This is only true when the variables are uncorrelated. And you can actually extend this beyond from summation to some other functions. For example, I have a continuous random variable x, okay, and its underlying distribution is known. Then I may introduce a function y as a function of x. Okay, this is a mapping. I am mapping a random variable x through a function f to define another function. Okay, so here is some example. So x is a random variable, I take log of that and I define a new random variable. So y is also a random variable here. Okay, and here I have written y is 1 by 2 pi x. Okay, so using this random variable I am defining a new random variable. Now the question is, when we do this, we generally know what is the distribution function for x. But now the next question is, having defined a mapping function, what would be the distribution function for the new variable? Okay, and this is what we call as a transformation of random variables. Using one random variable, you write a function of that into some other form, and you are interested in what is the distribution function of the new variable. It won't be the same. In this mapping, the distribution of x and the distribution of y are not the same. Okay, so we need to have a method by which we can find the distribution function of the new variable through some mathematical procedure. Okay, so before I show this, let me give an example. In chemical reaction engineering, we look at kinetics, reaction kinetics, and we know that the molecules have a kinetic energy. Okay, and then we know that the distribution of velocities are known. Okay, the molecular velocities are known from kinetic theory. From there, we want to find what would be the distribution of energies. Okay, why we are interested in the energy distribution is because we know that there is some activation energy for the molecule to react, and if the kinetic energy of the molecules are beyond certain threshold, they are likely to undergo reaction. So we want to know what fraction of molecules would have an energy equal or higher than the barrier, and this question depends on the temperature. Okay, when I have temperature, high kinetic energy, higher probability, higher number of molecules will have fraction of energies required. So there is a reason to find out what is the fraction of molecules having a particular energy at a particular temperature. Okay, so then what we are seeking is, if I know the molecular velocities of the molecules, there are three components of the velocities, and I want to write the kinetic energy as a function of this. Okay, so you can see that this is nothing but the kinetic energy of the molecules. So now I know the distribution of x1, x2, v1, v2, v3. Okay, this is a Gaussian distributed. Okay, kinetic theory gives you that. But what we are interested in is, if I define a function E which gives me the kinetic energy, what is the distribution of energy itself? Okay, so that's a kind of question we are interested in. So the mathematical procedure to do this is written here, that I have a variable y and I am interested in finding this distribution. So in this case, this y is energy E. This small y is the value of energy that it can take, the realization, the sample value, and this is a random variable. This x is in this case, the molecular velocities distribution function. This capital X is a random variable. It's a multivariate. It will have v1, v2, v3, and this is basically trying to find all possible velocities such a way that the kinetic energy will be equal to the specified value y. Okay, so this delta function will only sample those molecular velocities corresponding to the energy E that you want to specify. Okay, so this integral will basically map a set of x random variables into a corresponding y values. Okay, and so that expression is what now written here for this example. So here if you see, I am interested in this new variable E. Okay, to be more precise, I can write this as like this. Okay, I am interested in the distribution of energy having a particular value E. Okay, and this should also be E. So see, I am writing here V square. What I should be writing is this V1 square plus V2 square plus V3 square, but together I am writing this as just V square. Okay, so here I am integrating all V1, V2, V3 possibilities such a way that those combinations gives me the energy that I am looking for. Okay, it only selects those set of molecular velocities. What you see here is the distribution of velocity, which is Gaussian. So from here, if you operate this mathematical procedure, you will actually arrive at the distribution of energy. Okay, you can see that it is proportional to square root of E and also exponential of minus E by RT. It gives me, so now if I specify the temperature, I will know how the distribution of energy looks like. Okay, so this information is far more important than having this distribution alone, because this one will tell me what fraction of molecules will undergo reaction at a given temperature. Okay, you are talking about this one, right? See, this is not a Gaussian anymore, this is an exponential distributed, right? So the distribution of velocity is very different from the distribution of energy. Okay, only what we are saying is when I have, let's say, 1000 molecule, each of these molecules will not have the same energy. There is a distribution with which energy is distributed. Okay, so if I make a histogram of energies of all these 1000 molecule, and when I make a probability function, that would be just this. Okay, then you can ask what fraction of molecules would have energy E more than, let's say, 100 kilojoule per mole. Okay, you can ask that kind of question, and this expression gives you that. Then that gives you what is the likelihood of those reacting. Okay, because there is an activation energy barrier. Only those molecules having energy larger than the activation energy would actually jump the potential well. So So generally, when you have a simple one-dimensional random variable, and when you try to map it like this, you have one single random variable, and you are writing a function as y is equal to f of x. In this case, you can simply do an inversion if the function is invertible, as x is equal to g of y, and from here you can get the distribution. Or if you have more multi-dimensional one-to-one mapping, then you have to use this Jacobian determinant. You have to find the the derivative of each variable with respect to the other variables, and then you can also do this. Okay, so maybe I will do one or two examples later on in this this course. Okay, so there is a way, there is a mathematical procedure with which you can transform the random variables and get the associated distribution function. So that's the message. Okay, so we'll stop here.